Okay, we're going to create the trig identities, known as the Pythagorean trig identities, because basically the first one comes from Pythagoras' theorem. So once again, I draw in my unit circle on the number plane, and I can draw in a triangle. It makes an angle with the positive x-axis. We're saying it's the unit circle, so therefore the hypotenuse is equal to 1. From that, I can say, well, I know the equation of the circle is x squared plus y squared equals 1. And then I can read off the triangle, and I know, well, y over 1 would be the sine of theta, so y is sine theta. X over 1 would be the cosine of theta, so x is cosine theta. Substitute that back into the equation of the circle, and we get our first relationship. Sine squared plus cos squared, always equal to 1. So it does not matter the size of the angle. Sine squared theta plus cos squared theta, you'll always get the answer 1. So that's the first of the Pythagorean trig identities. To get the next one, if I divide each of those terms by sine squared. So sine squared over sine squared, which is of course 1. Cos squared over sine squared, which would be very good, cot squared. And 1 over sine squared, which would be cosec squared. So that gets our next relationship. 1 plus cot squared is cosec squared. But if instead of dividing by sine squared, I divide by cos squared, then we get sine squared divided by cos squared, which is tan squared. Cos squared divided by cos squared, well, that's obviously 1. And 1 divided by cos squared, sec squared. And so there's the third of our trig identities. So there they all are summarised. Sine squared plus cos squared is 1. 1 plus tan squared is sec squared. 1 plus cot squared is cosec squared. They are in fact all the same relationship as you just saw. It's just a matter of getting that first one, dividing by sine squared or dividing by cos squared, if you ever do forget. With those three, plus a special relationship, that we know that sine divided by cos is tan. Now that's not what we call a trig identity, but it's a relationship that certainly comes in handy with solving some of these problems. Remember, tan can be rewritten as sine on cos. If cos theta is 3/4, tan theta is negative, find sin theta. Now, the reason I put this in as an example is because you'll find it in the textbook here. I personally would not use the trig identities to go and solve this problem. I think there's a much easier way. They told me cos theta is 3/4, so I could draw up a triangle. Adjacent is 3, hypotenuse is 4. By Pythagoras, the other side would be the square root of 7. They want me to find sine theta. Well, I can just read off my triangle. Got to be careful though, because they've told me tan theta is negative. So if cos theta was positive 3/4 and tan theta is negative, which quadrant are we in? And so sine will be positive or negative?
Negative.
Negative is correct. So we're in the fourth quadrant. So reading off our triangle, the ratio is root 7 on 4, but we know it's in the fourth quadrant, minus. I think that's the easiest way of doing it. I think what they're expecting us to do is substitute into sine squared plus cos squared is equal to 1, rearrange that, and you get sine squared would be root, what would it be, 7 on 16. So then sine is plus or minus, and then you have to make a decision, oh, is it the plus or is it the minus? Yeah, I just think there's a little bit more work in that. So it's just easy to draw the triangle up and do it this way. Okay, let's look at some typical identity questions. We see 1 minus cos squared, same. Now, hopefully you do recognise it straight away. If you don't, the way to think about it is, oh look, I've got 1 minus cos squared. One of those trig identities involved cos squared. So if I rearrange that identity to make cos squared the subject, and I'll substitute in, so it was sine squared plus cos squared equals 1. So cos squared will equal 1 minus sine squared, and then I can expand that out, and oh, what do you know, I end up with sine squared. And so hopefully you just recognise 1 minus cos squared is sine squared. But the nice thing, I guess, about those three trig identities is none of the ratios are doubled up. So it's kind of obvious which one you got to use. Sec squared minus tan squared. Well, I got a relationship that says 1 plus tan squared is sec squared. Maybe I'll substitute that straight in. So 1 plus tan squared is sec squared. Oh, look, tan squared minus tan squared, 1. Tan theta cos theta. Hang on, there's no squares there. So when I see something like that, I start to think, well, maybe I'm not going to use one of the trig identities. Maybe I'm going to use that relationship that tan theta is sine on cos. So if tan is sine on cos, coses cancel, and we end up with sine theta. More typically, we get something like this, where they ask us to prove that one thing is the same as another. Now, you've got to be careful here. You don't want to be accused of fudging. That's the problem whenever they give you the answer. If you just jump to the answer and go, oh, look, I've got it. It's got to be clear how you got it. So you could start with the left, prove the right. You could start with the right, prove the left. You could work on each piece independently and show they're equal to the same thing, and then make a conclusion. Well, if they're both equal to this same thing, they must be equal. I think I just started with the left. All right, 2 sec squared minus 2, 4 tan theta. I see the sec squared. So the identity involving sec squared is 1 plus tan squared is sec squared. So the top of that fraction, if I put in 1 plus tan squared for sec squared, I get 2 plus 2 tan squared, but minus 2, I now just have 2 tan squared on 4 tan. Well, the tan and the tan squared will cancel, leave me with tan alpha on 2. So this is what I was saying. When we're doing our trig identities, it's a bit like those inequalities we were proving, the same sort of idea. We can't treat it like an equation to move things from side to side, because that would be assuming it's true. And we're being asked to prove it's true. So I can't do that. So start with the left-hand side, prove the right-hand side. Start with the right-hand side, prove the left-hand side, or work on each piece independently, show they're the same thing. But never, ever, ever do it like an equation, because that would be implying you're trying to find alpha. And because it's an identity, well, it's true for all values of alpha. We shall try exercise jolly good fellow, followed by 4F.